We're going to take a look at the 2013 free response questions 1, 2, and 3. Questions 1 and 2 do allow the use of a calculator, while question number 3 does not allow the use of a calculator. Let's begin by reading the prompt and identifying the key terms, and then we'll look at the questions and see how we use those key terms to answer the questions. On a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G of t, where t is measured in hours and t is between 0 and 8 inclusive. At the beginning of the workday, t equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation from 0 to 8 inclusive, the plant processes gravel at a rate of 100 tons per hour. So we see immediately we have two things going on here. G of t is the arrival rate, so that's really like your in rate. And then we have the constant rate of processed gravel. So this is the process or the out rate. The other thing we notice is that t equals 0, there are 500 tons of gravel sitting there and it's unprocessed. So we have an initial condition. In letter A, we're finding G prime of 5. So we're finding the rate of a rate. Now remember, G of t is already a rate, and G of t is measured in tons per hour. So when we go to G prime of t, remember a derivative modifies its preceding function. So G prime of t is going to tell us whether G of t is increasing or whether G of t is decreasing based on the sign of G prime of t. Also, G prime of t, since G of t is in tons per hour, G prime of t is tons per hour, and then we divide by time again, so that would be tons per hour, or tons per hour squared. So with our calculator, we're going to find G prime of 5, and we'll go to the scoring rubric to take a look at that. So G prime of 5 directly off the calculator, which would be math 8, is negative 24.588, or we'll take negative 24.587, either rounded or truncated, and there's 1 point for getting the correct value. The second point is the interpretation with units. Now in my class we would say at 5 hours, and this is the subject of the sentence. Remember, G of t is the rate at which gravel is arriving. So that is the subject of our sentence. That's what's being modified. So at 5 hours, the rate at which gravel is arriving is decreasing. We see the negative here by, now notice there's no negative in front of the number. The decreasing counts for the negative, 24.588 or 24.587 tons per hour, or tons per hour squared. In letter B, they want us to find the total amount of unprocessed gravel. So read your words carefully. We're only dealing with unprocessed gravel that arrives at the plant during the workday. So we don't need the initial condition because that gravel was already there. This is the amount of unprocessed gravel that actually arrives during the hours of operation. So we're going to accumulate. Remember, G of t was a rate. We're going to accumulate from 0 to 8. G of t, the calculator is going to do that work for us, and we get 825.511 tons. 1 point is for writing the integral correctly, and 1 point is for the answer that you get directly off of your calculator. In letter C, your question is the amount of unprocessed gravel. Now remember, we just talked about the amount of unprocessed gravel in the last question. Is the amount of unprocessed gravel at the plant increasing or decreasing at t equal to 5 hours? So we want to know if the amount is increasing or if the amount is decreasing. Well, if we want to know the amount and we want to know increase, decrease, we go to the rate of the amount. And the unprocessed gravel at G of t, sorry, so we're going to need to know what's happening with G. We need to know G prime of 5, and we're going to need to compare that to our processing rate because two things are happening at 5 hours. gravel is being brought in, so that would be the rate at which gravel is brought into the plant. But remember, we're also processing gravel at 100, I think it's tons per hour. So two things are impacting that. Where was that? In the prompt. There it is. The process rate, right back up here, is 100 tons per hour. So let's look at the scoring rubric. We're going to take a look at G of 5, which means we're going to go directly to the calculator. We're not going to do a G prime because G is a rate, and when G of 5 is 98.140764. And remember, the processing rate was 100, and since 98.140 is less than 100, then at time t equal to 5, the rate at which unprocessed gravel is arriving is less than the rate at which it is being processed. Therefore, the amount of unprocessed gravel at the plant is decreasing at time t equal to 5. In other words, we're processing it faster than we're bringing it in, so the amount of unprocessed gravel is decreasing. So for that question, you get 1 point for comparing G of 5 to 100. Now, the other thing that you could have done is you could have said the in rate of 98.140 or 1.1 if you rounded it, minus the out rate of 100 is less than 0. That's the same thing as comparing G of 5 to 100. So if you did it like that, you're perfectly fine. And then the conclusion should be that the amount of unprocessed gravel at the plant is decreasing. And then going back to letter D, good old extreme value theorem. What is the maximum amount, so that launches us into extreme value theorem, of unprocessed gravel at the plant during the hours of operation? Justify your answer. So we already know we have endpoints of 0 and endpoints of 8 because they told us those were the hours that the plant processes or receives and processes gravel. And we're going to need to know when the in rate, in other words, G of T minus 100, in rate minus out rate, is equal to 0, or when they're equal to each other. Remember, whenever you set those equal to 0, that's the same thing as really setting those equal to each other. Doesn't matter how you put that into your calculator, but you will need to make some adjustments on your window. So when you set right here, it tells us they're calling A the total amount. So this is really, A prime is really saying the student set the in rate minus the out rate equal to 0, or set them equal to each other, and they found the critical number. So the critical number that we are looking for here is T equal to 4.92348, and you would store that number. Again, that comes directly off of your calculator. And then we're going to need to accumulate the amount of gravel at the two endpoints. So at 0, there were 500. Our integral says take the initial amount of gravel that we had, add it to the amount that we process in and process, or bring in and process out. So we accumulate that on the calculator, accumulate to 8, and those are the numbers that we get. Now, I will say, because there is only one critical number here, and we were looking for the absolute, where's our answer? We were looking for the absolute maximum amount. So the absolute maximum amount occurs at the critical number. So in your writing, if you wrote up and explain that because by looking at the graph, if you did the graph of G of T minus 100, and you looked at that graph, you would be able to determine that the graph we're looking for, I keep forgetting what we're looking for, the absolute maximum. Let me write that down. Absolute maximum. So you would be able to determine from looking at the graph that from 0 to 4.92348, the derivative graph, the total derivative is positive from 0 to 4.92348, therefore the total amount increasing. And then you could look at the total derivative graph and see that from 4.92348 to 8, the total derivative graph is negative, therefore decreasing, and then you could explain that the amount of gravel at 4.9238 is greater than the amount at 0 and is less than the amount at 8, therefore. So you could do it paragraph style, and I think I might have some student work here. No. What I do have are College Board notes of things that they learned and recognized in this particular year. So what were some of the common student errors? In Part A, some students provided incorrect or no units. And for those of you who are in my class currently right now, you know that's something that we've been working on. It is a true shame if a student forgets to put units when units are required or requested. You're losing points, you're just leaving them on the table, and it's also not a great thing to put incorrect units. They said students had trouble interpreting G prime of 5, but we work on that a lot in our class. Okay, and in Part B, several students incorrectly included the initial amount of gravel in the net increase. So in other words, to determine the amount of unprocessed rock that was being brought in, we did not need the initial condition. In Part D, I'm right here, several students used incorrect presentations for the amount function. Probably there were students who probably forgot to include the initial condition in this part. Some students messed up the derivative. Most students who obtained a correct value for the maximum amount of gravel provided the integral setup. However, several students did not provide mathematical expression that led to their answers. So I want to remind everyone, we're taking a math test. We need to see math evidence. Few students were able to provide a complete, correct justification for a unique critical point. Many students provided only a local argument, and I have talked to you guys about that you can't just say the derivative graph changes from positive to negative. That just gives us a local. You have to rule out the endpoints. Based on your experience, what would you tell students and teachers? Keep practicing in rates and out rate is basically what they're saying, and that's what we're doing. Stress the importance of showing work. In particular, the mathematical setups. That is very, very, very important. Moving on to question number 2, we can very quickly see that we have a particle problem. We've been given a velocity function, and the position of the particle is given by s of t. So they're giving us the name of the position function, and they're giving us the initial position to be used or maybe not to be used. Could be extraneous information. Find all values t from -2 to 4 for which the speed of the particle is 2. So speed is absolute value of velocity, so we're going to do absolute value of v of t equal to 2 on our calculator, or you could do v of t equal to -2, v of t equal to +2. That's the same thing. So in your calculator, if you had this v of t into y number 1, then for y number 2, you could just put absolute values around y1 and then figure out where that graph intersects with the line y equal to 2. So that's a real easy question, although recently in our class we had one like that and a lot of students set velocity equal to 0. So you can see that there's 1 point for the student using the absolute value of velocity and showing us that it's set equal to 2. Answers cannot magically appear. We have to see the setup of your work. This is the bare minimum that you would show us, and then after that your answers can appear. In letter B, we are writing an expression involving an integral, so they're telling us straight up, use an integral that gives us the position. Use this expression to find the position at t equal to 5. Remember, position needs position, meaning when you're writing the position function, you need the initial position. So they told you that at 5, sorry, no, we're finding 5, I apologize. They told us that there were 10 units of area already accumulated, and that occurred at time t equal to 0. So that is where we begin the accumulation of area, and they want us to figure out how much area we accumulate. The calculator is going to do this for us. I'm again assuming that you have v of x in y number 1, and you get negative 9.207. You get 1 point for the position, writing the position function, and that would be here. So pay attention to that. They asked you specifically for the position function and then the position at t equal to 5. Notice the variable disagreement. We've had that conversation before. So we want a function in terms of t, so the t is the upper bound, and then we use that x as the dummy variable. Moving on to letter C, find all times t in which the interval from 0 to 5 at which the particle changes direction. So if we want a change of direction, we know that we're going to examine velocity. So for change of direction, v of t changes sign. It's not just a touch of the x-axis, it has to change sign. So there's my justification already. So on my calculator, I'm going to figure out where v of t, already in my calculator, equals to 0, and I get two values here and here. You don't really have to say changes from negative to positive, but it gives a little stronger argument. But basically, v of t changes sign at that time, and v of t changes sign at that time. But it's not bad to give that specificity to your reasoning. So 1 point for showing us that you're setting v of t equal to 0. Again, ladies and gentlemen, it's a math test. You have to show setups, and then your answers with the justifications. And then lastly, letter D, we're back to speed again. So you can see by now that speed is an important concept. Is the speed increasing or decreasing? Now we know this very well. Speed, if I'm speeding up or slowing down, I have to look at two components. I have to examine the velocity at t equal to 4, and I have to examine the acceleration at t equal to 4. If these two numbers have the same sign, then we are speeding up. If they have opposite sign, then we are slowing down. Very important, and you can see it comes up on the AP test. So we're going to use our calculator to find v of 4, and we're going to use our calculator to find the derivative of v at 4. We can see that they have the same sign. Therefore, we're going to say that the particle speeds up because velocity and acceleration have the same sign. 2 points for the conclusion with the reason. All right, and the last problem in this video is question number 3. Let's look at the common mistakes. In part A, students did not consider the absolute value of the function. We've seen some of you have trouble with that in a recent problem in our class or a quiz. They set v of t equal to 2, so please don't be this student. In part B, students had difficulty writing the expression for s of t. These students often included a definite integral. In other words, they told you that they wanted an equation. An equation has variables in it, so this is what they're talking about. This had to be here to get the s of t points. Down here, this is giving you a specific value. It's not an equation, it's a value. And in part C, most students did consider the equation v of t equal to 0 in order to locate the times when the particle change directions. Of those students who considered this equation, most were able to find the two values. I'm just looking for anything that would be big that you need to know. Well, some students messed up with speed because a lot of students forget to look at velocity and acceleration. So down here, based on your experience of student responses, what message would you send to teachers that might help? Students need to understand the relationship between speed and velocity. I have stressed that to you guys. Teachers should remind students that even though sign charts are wonderful organizational tools, there must be a related written interpretations. We do not grade sign charts, and I've made that clear to you. Clear, concise mathematical communication is very important. Again, let me say that. Clear, concise mathematical communication is very important. Students should not refer to functions using the words it, the function, or the graph. Said that to you 1,000,000 times. And then question number 3. We have our table problem. And in this problem, hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup from 0 to 6 inclusive is given by a differentiable function c. So this is the amount of coffee measured in ounces. Selected values of C of t are given in the table as I just indicated. Use the data in the table to approximate C prime of 3.5. We know that 3.5 is between 3 and 4, so we're going to go one data value above, one data value below. We're going to show a difference quotient of 12.8 minus 11.2 over 4 minus 3, and we're going to take our hands off. We're not going to simplify, and then we'll get this answer right here. And since we're finding the derivative, that would be ounces per minute. And so 1 point for the approximation and 1 point for the units. In letter B, is there a time? So we know that we've now launched into a theorem. The question is, they don't say absolute maximum, so we know it's not EVT. So the question is it IVT or MVT, which possibly we know that Rolls is a special case of the MVT. So I'm looking here at C prime and instant rate equaling 2, and then I need to go back up to my table to make sure. So yes, in this table, this is C of t. So we're going from C to C prime, which is the derivative. So it's asking, is the instant rate of change from the interval 2 to 4 equal to 2? Well, let's go back up and look at the words of our prompt. We know that we have a differentiable function c, and differentiability implies continuity. So we have our conditions met for the mean value theorem because we have a function that's continuous on the closed interval from 2 to 4 and differentiable on the open interval from 2 to 4, which needs to be stated before we can finish the theorem. Then we're going to find the average rate of change because mean value theorem says if the conditions hold true at least once, the average rate will equal the instant rate. So from 2 to 4, let me change colors here. So from 2 to 4, we have 12.8 minus 8.8 over 4 minus 2. And so let's look at the scoring rubric. So we have C is differentiable, it's everywhere. C is continuous everywhere, and specifically on the closed interval from 2 to 4. When we calculate the average rate of change, which is what I was doing at the top, the average rate of change is 2. Therefore, by the mean value theorem, and you don't have to quote the theorem, there is at least one time in which the derivative is equal to 2. 1 point for calculating the average rate of change and 1 point for the conclusion using the mean value theorem, and that conclusion includes you stating the conditions of the theorem. Remember, they told us they want concise, good, clear answers. In letter C, I'm going to clear the board right now. So in letter C, use a midpoint sum, and this was something that several of you had struggled with on our last quiz, with 3 subintervals of equal length indicated by the data in the table. And they want us to use the midpoint sum to find the accumulation of area from 0 to 6, but we're actually going to be finding an average value. So I'm going to start with the midpoint sum, 3 subintervals of equal length. So 1 rectangle goes here, 2 rectangles, 3 rectangles. So we have a common width of 2, 2, and 2, and we have a midpoint number 1, that's the first height of the first rectangle. Midpoint number 2 is the height of the second rectangle, and midpoint number 3 is the height of the third rectangle. So we'll have 1/6 of 2 times 5.3 plus 2 times 11.2 plus 2 times 13.8, and then they want us to use interpret and use correct units to explain that. So here's the work. I don't care about this line right here. We're going to have our 1/6, and we can see the midpoint sum, the common height 2, 2, 2, midpoint 1, midpoint 2, and midpoint 3. So that gets you the first 2 points of the midpoint sum as well as the approximation. You do not need to take it at all down here. Then we have to interpret. So we will say this is the average value of C of t, and C of t was the amount of coffee in the cup. So the average, you could say value of, the average value of, or the average amount, because C of t is amount of coffee in the cup, the average value C of t in ounces from 0 to 6 minutes. And then lastly, letter D, the coffee in the cup is modeled by a function b of t. Use this model, or using this model, find the rate. So b of t is amount, and we want the rate that the cup, or at which the amount of coffee in the cup is changing when t equal to 5. Now remember, this is no calculator part, so we have to find the derivative by hand. So the derivative, let's come back up here. The derivative of 16 is 0, and the derivative of e to a power is e to the power times the derivative of the power. In other words, negative 16 e to the power multiplied by the derivative of the power. So this is the power, and the derivative of negative 0.4t is negative 0.4. And now when we find the rate at 5, all we have to do is substitute 5 in place of t and leave it alone. We do not have to simplify it. We do not have to multiply it. We don't have to do anything to it except substitute the 5. So right here, this would be the answer that I would expect you to leave with your units. Now there's no unit point for this, but there's 1 point for b of t, which is right here. It doesn't have to be clean. It can be unclean. In fact, this is what I would expect. This is what I would give you 1 point for. And down here, you also don't have to have 6.4. You could substitute the 5 in here and be done with it, and that would give you the b prime of 5 point. All right, so I hope this helps you to figure out any mistakes that you made and strengthens any kinds of questions you might see in the future.